Okay, and we have Simone. Okay, so today we're happy to have two speakers. We have Simone Ferraro and Colin Hill who are going to tell us about DESI and ACT and just the state of cosmological data in general. I wanted to just lay out the kind of plan in terms of schedule because it's an unusual meeting. So we're going to have each speaker has been given 15 minutes, 10 minutes to overview the sort of big picture of the data. They're going to give 5 minutes of their own kind of perspective on what they find interesting or provocative in the current data. So that'll be about 30 minutes. The plan is then to have a 20-minute moderated discussion where I will pose questions that I think will be interesting to this community. If there are clarifying questions along the way, please either put them in the chat or if the chat's being ignored, but you can unmute and ask. I think clarifying is important and along the way if we're missing anything. And then the last 10 minutes will be open to questions for everyone. But I wanted to make sure we had a time where it wasn't, we got to hear sort of some back and forth between the speakers without it being too free for all on a Zoom that might have a lot of people. So just so if you have kind of just like, I'd love you to explain this thing, but it's kind of not being discussed, save a question for the end. If you want to put it in the chat beforehand so that we kind of like, you get your priority, like I really want someone to talk about this, please feel free to do so. Okay, with that in mind, we didn't actually settle who's going first. So Simone and Colin, who wants to take the lead?
Either way, it's fine with me.
Okay, since you spoke up, it's your territory. So Colin, we're going to start with
Great.
Colin talking about ACT. Did we already give sharing permissions? Okay, good.
Looks like it's working. Can you see that?
Yep, looks good.
Okay. Okay. Great. Well, yeah, thanks a lot for having me. I'm Colin Hill from Columbia. I'm going to tell you about just a few of the interesting things from our recent set of papers as part of the Atacama Cosmology Telescope, or ACT Data Release 6. If you want all the gory details, it's in this series of 3 papers that came out in March. And most of the stuff that's relevant to this crowd is probably in this paper that I co-led with Armenia Calabrese on beyond lambda CDM cosmological models. All right, so I know that we're mostly theorists here, but I'm going to just quickly show you some of the data because it's just incredible, and I'd like to make sure that you're all aware of just how beautiful it is. Okay, so first, let me introduce you to ACT, in case you haven't heard of it before. So ACT was a 6-meter telescope on Cerro Toco in northern Chile. So it's a ground-based CMB experiment. It collected data through 2022, and the bulk of our most sensitive data was collected in the last 5 years of the survey, and that's what comprises the DR6 data release. As you know, the Atacama Desert and South Pole are the 2 best places on Earth to do ground-based measurements, and we're continuing to build new instruments at this site, which I'll briefly touch on at the end. Okay, so you might have the impression that from the ground we only observe small patches of sky, but that's no longer the case. So DR6 from ACT covers almost half of the sky. This is a large fraction of what you can see from Chile. Our noise levels now have dropped below those of Planck. In fact, in polarization, we're about a factor of 3 more sensitive than the Planck data, which is why this is such an exciting measurement. We don't measure the largest angular scales particularly well from the ground because of atmospheric noise, so it is still very advantageous for us to combine with the satellite data to get the full range of angular scales in the power spectrum. So the results I'll show you for the power spectra are estimated from the cleanest, roughly 25% of the sky after we mask out the Milky Way. All right, so let's look at some of the maps. This is Planck, not ACT yet. So this is Planck in total intensity or temperature. I'm just zooming in on a small patch that's about 100 square degrees here. As I'll then show you in a second, we're going to add in the ACT data to make a combined map that has better sensitivity. So here's what it looks like after you add in ACT between these. But effectively, you can see that we resolve the small angular scales much better than Planck can, a much larger telescope. And you can also pick out individual objects at these frequencies that Planck can't resolve, like nearby galaxies. This is the Sculptor galaxy, AGNs, and also TSZ galaxy clusters. So lots of rich science here, but I'm just going to focus on the CMB. Here's polarization. So this is Planck in E mode polarization. This should look like noise to you because this is a noise-dominated map. Here's what it looks like with ACT. So we go from basically a totally noise-dominated measurement to a signal-dominated measurement. So our gains in polarization are just absolutely enormous. In some sense, this is kind of like the gain going from WMAP to Planck in temperature. Now going from Planck to ACT in polarization is sort of a comparable gain in sensitivity. Okay, so here's what the full footprint looks like. This is, high signal to noise, E-mode polarization measurements on almost half the sky, and you can see the thermal dust from the Milky Way in this band here. Okay, and let's go ahead and take a look at the power spectra. With high sensitivity comes very rigorous tolerance for systematic effects. So it took us a few years to work very hard to make sure we understood all the different systematics, which I'm not going to talk about here. We did a blind analysis and we opened the box internally about 1 year ago this month or last month. All right, so here's the power spectra. This is taking a look first at the temperature power spectrum. The orange points here are from Planck. So Planck is a fantastic measurement of the TT power spectrum up to L of say 2000 or so. And then here's what it looks like when I add in the ACT data points in blue. So you can see that on the range of angular scales where we have overlapping sensitivity, there's excellent agreement between the two measurements. And then what ACT can add is to measure the small angular scale, the so-called damping tail CMB power spectrum at very high sensitivity, where there's sensitivity to new signals. Here's the E-mode polarization power spectrum. So Planck again in orange. As you can see, there's lots of noise, consistent with what I showed you in the map a second ago. Now here's what it looks like with ACT. So there's just a phenomenal improvement in sensitivity. Again, we agree well on the range of scales where we both have sensitivity, but then ACT lets you measure this out to much, much smaller scales. And in fact, we have smaller error bars in EE basically on all scales for which we can make measurements from ACT. Okay, and then lastly, here's the TE cross power spectrum. Planck again in orange, and then here's what it looks like when we add in ACT. So again, excellent agreement, but now we can measure this out to basically the whole range of scales to where it starts to go to zero. One fun fact is that the TE power spectrum is in fact so sensitive now that with just this one observable, you can constrain H naught, the Hubble constant, to about 1% precision within the context of lambda CDM. So yeah, just beautiful data. Okay, so then let's fast forward and start talking about the cosmological implications. You should note that everything I just showed you there was after we've performed foreground cleaning. I'm not going to talk about that, but it's something that I have spent many years of my life working on. So if you want to know the gory details, feel free to ask about it. Okay, so let's fit the lambda CDM model first, the standard model. It's always the starting point. So the first takeaway message is that lambda CDM provides a very good fit to the ACT-DR6 data. It also provides a very good fit to Planck, as we already knew. But a new fact is that there's a consistent lambda CDM model that describes both Planck and ACT quite well. That's what I'm showing you here. The residuals to the data points are in the bottom panel, and you can see that they scatter nicely around zero. And if you're a statistician, the PTE values are down here. It's a very good fit. Here's what it looks like in TE. Again, lambda CDM fitting the data quite well. And then lastly, here's what it looks like in E-mode polarization. And you can now very clearly see the statistical power of the DR6 data compared to Planck with these small error bars. But lambda CDM is fitting quite well. We can then take a look at the actual parameter constraints that come from doing that. So I'm showing you here the subset of the four parameters in lambda CDM that ACT constrains independently of Planck. Our measurement of the scalar amplitude AS and the optical depth tau, those are somewhat correlated with Planck, but these other four parameters, omega B, omega CDM, NS, and H naught, are effectively independent. And what you can see is that the posteriors overlap quite nicely. Formally, the agreement is at the 1.6 sigma level. So an interesting thing you can then try to do is to take that inference, which is based on fitting the primary CMB data, and then predict low redshift statistics that we can measure and see if it actually matches the measurements. So here's two examples. This is the CMB lensing power spectrum on the left and the DESI DR1 BAO distance redshift relation on the right. And the orange and dark blue dashed curves in these panels are not fits to these data. These are predictions based on the primary CMB lambda CDM model. And you can see that they go right through the data points. The VAO is, slightly off in this one bin, but formally the PTE is still quite good. So we're doing this end-to-end test of the cosmological model, extrapolating, 10 billion years forward in time, and it matches these measurements quite well. So you can then do a joint fit where you fold in the lensing data and the DESI BAO data to do a joint constraint on the parameters of lambda CDM, and these are the results that you get when you do that. So P act LB means Planck plus act plus lensing plus BAO, and that's our sort of state-of-the-art combination. And it gives you these purple contours. So the H naught value from doing that is 0.5% constraint centered at 68.2. So this is a low value in the context of the H naught tension, which I'll come back to a little bit later. All right, so let me turn then to talking about constraints beyond lambda CDM. This is just a very small sampling of what's in this paper. We looked at a very wide range of new physics models here. So something that I think is probably of great interest to this crowd is constraints on the primordial scalar perturbation power spectrum. So for the first time, we can constrain NS, the scalar spectral index, to comparable precision to that of Planck without using any Planck data. So this is WMAP plus ACT, and you can see that we make a measurement that's in excellent agreement and confirm the deviation from scale invariance at about 7 sigma. So you can then fold this into the inflationary zoo plot, where the constraint on the tensor to scalar ratio here comes from bicep data. That's not from ACT, that's from bicep plus Planck. But the ACT data provide significant tightening of the NS constraint on the x-axis. So the purple band here is P-act LB, as I highlighted a minute ago. So you see that NS has moved up by about 2 sigma compared to the best fit from Planck, which is orange. That's about roughly half coming from ACT and about half coming from DESI. So about 1 sigma from ACT, 1 sigma from DESI. You may find this interesting. You may find it to be a statistical, I don't know, curiosity that it moved up by a little bit. It's not highly significant, but it does slightly change the preferred picture in terms of the inflationary landscape. So the Starobinsky model is down here, and this is for n equals 50 to 60 e-folds of inflation. You can see that it's now slightly outside of the best fit range. So could be interesting to think about the implications there. We also looked at possible evidence of departures from a power law in the primordial scalar power spectrum. So that's what's shown here. We didn't detect any so-called running of the spectral index. You can see that the purple band here fully encompasses the usual power law, which is the dashed black. And the constraints are about 30% tighter than previous measurements. We also looked for isocurvature perturbations and tightened constraints on those. We did not detect any deviations from adiabaticity. One thing that might be of interest, which I've added here, this is not in the DR6 papers, but this is a forecast for an upcoming measurement that's still work in progress, is a measurement of primordial non-Gaussianity with ACT-DR6 combined with Planck. And here are constraints, forecasted constraints on the different shapes of the 3-point function. Roughly speaking, the gains over the Planck measurement should be about 25% for these different parameters. So this will give us new constraints on possible self-interactions of the inflaton, multiple fields during inflation, non-bunch Davies vacua, etc. So stay tuned for that. Yeah.
We have a question in the chat, which is, did you do a primordial features analysis similar to what Planck does?
That's an excellent question. We did not do that in the DR6 papers. I think that would be a very interesting thing to do. Yeah.
I will pre-ask this question of Simone about the DESI primordial features analysis, so Eva doesn't have to write it in the chat. But
should I answer
that? We'll wait for your talk when we've gone through your data. But yes, you can feel free to add it in there. But yes, okay. Sorry, Colin, continue.
No problem. Yeah, someone should do that. I hope maybe it'll be some of us. I don't know. Okay, let's then turn to new physics in the later universe. So a couple updates on potential evidence or constraints on free streaming dark radiation or light relics. So these are parameterized with this parameter n effective, the effective number of relativistic species. In the early universe, the standard model predicts a value of 3.044. You can see that we're consistent with that. We fluctuate a little bit below 3. This is the posterior in purple here. it fluctuates down a little bit compared to the Planck constraint in orange. If you add in BBN data, assuming that n effective is the same at the two epochs, then it tightens up by about 20% to this 2.89 plus or minus 0.11. And these are the tightest constraints on n effective in the literature to date. You can then translate that to constraints on possible types of new particles that might have been in thermal contact with the primordial plasma. And one kind of benchmark thing we've been able to do is to push the constraint on spin 3/2 particles back through the QCD phase transition. So any light, by which I mean mass less than 1 electron volt or so, any light spin 3/2 particle must have been decoupled from the plasma sometime before 1 gigaelectron, a temperature of 1 gigaelectron volt. I'm sure that Simone will tell us about neutrino mass. We don't see evidence for non-zero neutrino masses, but that constraint is mostly driven by non-ACT data. All right, let me turn to some results on dark energy. So first, this is so-called early dark energy. So models in which there are some new type of scalar field that's present in the early universe that briefly accelerates the expansion, becomes dynamical around recombination, and then this affects the sound horizon in the CMB. This is a model that received a lot of attention in the H0 tension context. So this is the potential that has been popular. It looks like an axion potential, but raised to this higher power. N equals 1 would be the axion, but for various reasons that does not work. So we take values of n equals 2 or n equals 3 in this work. And we parameterize the model with 3 parameters, one of which is the maximum fractional contribution of this EDE to the cosmic energy budget, which is reached at a redshift ZC. So this is the evolution for a benchmark model of the fraction of the cosmic energy budget in this new field. So those are 2 of the parameters, and then the third parameter is the starting position of the field on its potential on this sort of wacky 1 minus cosine cubed potential. All right, so then here's the results. We had seen a hint at about 2.5 sigma of something like this early dark energy in our previous ACT DR4 data. In the DR6 data, this hint has now gone away. So the results are in these posteriors, the most interesting of which is the bottom right, where you can see that the FEDE parameter peaks right at 0. If you don't like Bayesian posteriors, you can do a frequentist analysis, and the maximum significance of this new EDE stuff is about 1.7 sigma, so not significant. And Dennis Leverby read a nice little summary of this in the New York Times. That's fun to quote. Okay, let me look at late time dark energy quickly. The primary CMB doesn't really give us much additional leverage on late time dark energy, apart from changes to the best fit values of the matter density, which then correlates with preferences in the late universe data for dark energy or not, for evolving dark energy, I should say. So this is a plot using the DESI DR1 data. I'll talk a little bit in a second about DESI DR2. As you probably remember, DESI saw a hint at 2.5 sigma in their year 1 analysis of evolving dark energy. When you add in ACT to that combination, it goes back towards lambda CDM by about 1/3 of a sigma. So not a huge shift, but it does push it slightly back towards lambda CDM. Okay, so let me summarize quickly before I tell you about a couple of my own personal thoughts. So this is a summary plot on H0, looking at a bunch of different new physics models, some of which I mentioned, like EDE, compared to the direct measurements from Rees et al., that's the shoes measurement here, or the Friedman et al. CCHP measurement. And what you can see is that we do not find a big shift in H0 in any of these new physics models. It's usually on the order of a sigma or less. So we don't detect any of these extensions. If we did, it would have been big news. So shoes remains in significant discordance with not just lambda CDM, but also a huge range of extensions to lambda CDM that we've been looking for. So another way to spin this is that we have the tightest constraints on a huge class of BSM scenarios from the CMB. And I'm sure there's clever additional things that one can constrain that we didn't have time to, which I would encourage everyone to think about. Okay, in the last -1 minute, let me tell you about some of maybe the curiosities or hints, my own views on the current situation. If you're a fan of the look elsewhere effect, you would think, well, we looked at dozens of models. You should have seen at least one hint of something at 2 or 3 sigma. So there was at least one of those. So this is a model where the growth of structure is modified. F here is just the logarithmic rate of growth. So the derivative of the growth factor D with respect to log A. It's canonical to model this as a function of the matter density omega m. General relativity predicts that this parameter gamma should be 0.55, very close to that. What we find is that there's a small preference for a value of gamma that's higher than 0.55, which corresponds to a slight suppression of the growth of structure. It's mostly driven by non-CMB data. There's these two outliers in this plot here that come from peculiar velocity surveys at low redshifts that suggest this sort of suppression of the growth rate. But even if you discard those points and just only fit the P-ACT-LB combination, you do find a slightly higher value at about 2.2 sigma. So for me, this is still just a curiosity. It is kind of interesting that if it is something new, it's also at late times, which is where there's hints of something new coming from the, time evolving dark energy. So perhaps an interesting clue. Let me skip cosmic birefringence. We can come back to that in the discussion if people are interested. And I'll just wrap up with one plot here looking at DESI DR2. So the DESI DR2 results that Simone will tell you about came out the day after ACT DR6 back in March. We've, of course, looked at it since then. So if you take the best fit lambda CDM model to the P-ACT combination and then compare it to the DESI DR2 data points, you actually find pretty good agreement. The PTE value of that is 13%. That's the dark blue dashed curve here. Planck lambda CDM famously does not agree very well. That's the orange dashed curve. Just the other day, 2 days ago, there was a paper from DESI themselves looking at a joint analysis with ACT and Planck, and their preference for evolving dark energy drops to 2.4 sigma when they include the ACT data in this combination. So to me, this kind of maybe is a big grain of salt to be taken with any hints for evolving dark energy, but I'm sure Simone will have more to say about that. So I'll stop here. The basic takeaway from DR6 with ACT is that lambda CDM is providing a very good description of the early universe, including measurements of the E-mode power spectrum that are far more sensitive than anything people had observed previously. So it's a very non-trivial test of the model. We don't see hints of any of these BSM scenarios that we looked at, and I'd say models that could have affected the H-naught tension by changing the sound horizon, for example. We're not seeing any evidence of those. So stay tuned. In the coming years, we'll have even better data coming from the Simons Observatory, which has been built at this same site in Chile. And I'm happy to take questions. Thanks.
Thanks, Colin. I didn't see any urgent questions on the chat, and so maybe to get to the discussion, we can move to Simone.
Sounds good. So let me share 1 second. PowerPoint. Okay, can you see correctly? Perfect. Hi, everyone. I'm Simone from Berkeley, and I'll give you the large-scale structure take on this, or at least my take. I should say I'm a member of both DESI and ACT, but here I don't represent either, so I can give you my own point of view. Okay. So you might have heard, and Colin kind of mentioned it, there was some, all sorts of press releases coinciding with the DESI data coming out, because there seems to be some, cracks forming in the standard lambda CDM scenario from late time data, so we can discuss what that evidence is. But first of all, what is DESI in 10 seconds? It's a large galaxy survey, spectroscopic, so you get three-dimensional positions, and it has a lot of different galaxy types with different funny names that I can describe later if you're interested. However, you should keep in mind that they cover the redshift from very local galaxies, very low redshift, all the way to redshift 4 with the Lyman alpha 4. So we have really a very large redshift level arms, and it's different type of galaxies with their own personalities, but I don't have time to go into that. However, the measurement I will talk about today is the measurement of the baryon acoustic oscillation. You're probably all familiar with it. Initial perturbations left over by inflation and reheating. Sound waves propagate out of perturbations, and they propagate until decoupling. So there is the sound horizon. The decoupling is a preferred scale in cosmology. It's imprinted in the galaxy distribution. And you can look at this scale, which is RD the drag scale, either perpendicular to the line of sight, and in this case, what you measure is some angle. Physically, you measure some angle, and that is just by simple geometry, the scale divided by the angular diameter distance, dm. Here's dm, and primarily depends on omega matter. You can also play the same game in redshift, so you can ask what the delta z, what change in redshift does the BAO scale correspond to? And as you know, if you want to translate the distances to redshift, the Hubble constant is, or the Hubble parameter in this case, is the conversion factor. Okay, so you can measure both RD over dm and RD times h of z. Those are the two primary quantities that we measure. So this is what it looks like for all of those different samples of galaxies at different redshifts. Usually just look at the top panel. That's the monopole of the correlation function. You see a peak in all of them. And it's actually quite easy and quite robust to centroid this peak. We actually marginalize over the detailed broadband shape. And therefore, while galaxies are complicated, we think this is the most robust thing that you can measure from galaxies, because we are marginalizing most of the personality of these galaxies in the same sense that all we are doing is we are fitting for this one single scale. And the DESI team was being very careful and run hundreds of tests, and we think we can do this extremely well, and is extremely independent of galaxy formation physics, of nonlinearities, etc., etc. So as far as galaxies go, I think this is the best you can do in terms of robustness. Okay, let's take a look what the data looks like. So again, this is the plane that is best constrained by the BAO, omega matter, and H naught RD. We start with the sample closest to us. You see big degeneracy. However, as you include more and more sample going up in redshift, you'll see something interesting happening, that the contours rotate, right? So I'm gonna go up in redshift now and include the various samples one by one. You can see kind of general consistency between all of them, and then you go to the quasars, quite high redshift, and finally the Lyman alpha forest. So you see each sample independently gives quite is not very tightly constrained. However, when you combine all of them, you get these small contours down here. Okay, so here you see the magic of having this redshift lever arm in breaking degeneracies between these parameters. So in the end, you end up with CMB free measurement about 3% on omega matter, and H naught RD about 0.7%. Okay, this is quite remarkable. So now, since this CMB free, of course, the first thing you can ask is the early universe consistent with the late time universe? So you can compare with the CMB. CMB here is a Planck in purple, or pink, I should say. This was the DESI year 1 BAO. The DESI year 2 is fully consistent with the DESI year 1, but it's in about 2.3 sigma discrepancy in this parameter space. And this discrepancy is precisely what will turn into sort of preference for dynamical dark energy later. So it's good to keep that in mind. All right, so what about, again, dark energy? So then, okay, there's a bit of discrepancy. So we in lambda CDM. So can we fix that with, say, some time evolving dark energy? So this, again, the DESI alone, does have some mild preference for, W. So of course, cosmological constant would lie here, W naught -1 and WA is 0. It's a mild preference for time evolving dark energy, but this evidence is at 1.5 sigma. So it's not dramatic evidence from DESI alone. DESI is still kind of consistent with lambda CDM. It's just a slightly different lambda CDM from what the CMB wants. So if you combine DESI and the CMB, now you get a stronger preference around the 3 sigma level. And as Colin said, once you include ACT, this preference goes down to around 2.5 sigma. Which has become paper from very, very recently. This conclusion is supported by the inclusion of supernova data. It's a sample that is a little bit more complicated to interpret, so I'm happy to talk about it. I have backup slides about supernova, but depending on which sample you include, this evidence varies between 2.8 and 4.2 sigma in terms of time evolving dark energy. If that's the correct, of course, that's a big if that's the correct way to reconcile large-scale structure and CMB measurements. Okay, so then BAO measures H0, RD, and omega matter, and RD is a function of this primordial quantity, omega matter is squared, so omega BA squared. If you take omega BA squared, you can get a CMB-free measurement of H0 and check the CMB. And in the context of the Hubble tension, it's quite interesting. So there's the CMB. Here's DESI, finds slightly higher value of H0. That's consistent, though, still with and it's still in tension with shoes. You can do a bit better when you include just the angular size of the sound horizon from the CMB rather than the parameters themselves, and this the orange contour there. So now you can see, CMB in lambda CDM, CMB versus BAO, predict CMB has slightly higher omega matter, slightly lower H0, and this will come up in a moment when I discuss neutrinos as well. So it's important to note. Okay, so I'm done with dark energy. I have something to say about neutrinos, so I don't know if this is a good time for questions or so far. Maybe let's discuss later, because I want to say a few things about neutrinos. So here's a very similar plot to what Colin already said. At face value, if you take a lambda CDM cosmology, you get really, really tight bounds on neutrinos once you impose a positivity prior for their mass. However, this is quite a bit relaxed in a W0 WA CDM, where you allow enough flexibility to the daytime expansion. You can actually weaken these constraints quite a lot, so they are model dependent. However, there's something a little bit more. So let's talk about lambda CDM. Okay, so until proven contrary, Colin just told us lambda CDM is a fantastic theory, matches the 30 plus measurements that they've made. So that's a good starting point. Okay, so this is a bit suspicious. So this blue curve is about twice as tight as a Fisher analysis would predict, right? And so unfortunately, this is a kind of here's where I can say I disagree, if you want, with some of the papers from some of the large collaborations in in the way that some of these results are presented, and it's because this should be a hint that maybe there's something going on, and you can't take just this as a face value and start discussing, what's the likelihood ratio of normal versus inverted hierarchy, and discuss about all sorts of neutrino properties or properties of the dark sector, because you should remember that this is a really indirect measurement. Okay, so far mu is a model parameter, okay, that modulates both the amplitude and the expansion history, amplitude fluctuations and the expansion history of the universe, right? It can only be interpreted, this parameter is only the physical mass of neutrinos, both if our data, if our model is correct, so lambda CDM is correct, and if all our data is free, consistent with each other and free from systematics, okay? So these are two big ifs. And also the other thing is that noise and systematics can have any signs. The question is, until you're sure that all your data is consistent, does it even make sense to put a positivity prior, or does it hide possible problems? And this is, I'm hinting at my opinion here, of course, is that I think we are in a regime where this positivity prior actually does hide the potential problems. So luckily, it took actually Dan and others to point this out explicitly. Internally, some of us were fighting for having that sort of in the main papers, but we lost that battle. Anyway, now it is in the year 3 papers, so you can extend the posterior for neutrinos to negative mass, no longer apply positivity prior. So now I said you need to make sure that both the data and the model are consistent before you call this variable actually physical value of neutrino mass. And the fact that within lambda CDM, neutrino mass, the minimum mass normal hierarchy of 0.06 eV is excluded at over 3 sigma. That hints at some sort of internal inconsistency, either between the data or with the model or both, right? So I think there is some internal inconsistency that we are worried about. So I would say that any inference on the value of neutrino mass at present, my personal opinion, is premature because of this inconsistency. Of course, a W0 WA cosmology alleviates this, but of course, there's not a proof that W0 WA is the correct model, and I don't think again we are there yet. So I think it's important to keep an open mind and consider all possibilities. I think it's fair to say that we don't know yet. There's something that doesn't quite fit, but we don't know yet what that is, and it's important to keep an open mind. So in the last couple of minutes, I just want to show something a little bit more speculative, but I think it's interesting nonetheless. Of this example of keeping your mind open to all possibilities. So we put our Berkeley team put out a paper called "Disputable: The High Cost of Low Optical Depth." We are referring to the optical depth to the CMB, which is by far the least well constrained lambda CDM parameter, and also the hardest to measure. It's measured to the very low L, meaning L of 6 or so in the Planck polarization data. So that's an extremely challenging measurement experimentally and data analysis wise. And actually today there was a very related paper by Wayne Hu's group as well, kind of reaching similar conclusions. So we just asked, what if we lived in a universe with a slightly higher optical depth, for example, an optical depth of what WMAP had found back in the days, now I should say this slightly higher optical depth is completely at face value ruled out at the 4 sigma level by Planck. But if there was some problem with Planck measurements, now the parameters measured by BAO and CMB suddenly agree between CMB and large-scale structure. Neutrino mass is positive and consistent with normal hierarchy. Dark energy as a cosmological constant is completely fine. So one thing that maybe some people in the field know, but it's important to realize is that tau affects almost all parameters inferred from the CMB, not just neutrino mass. It's been discussed previously in terms of neutrino masses, but it affects omega matter. It's extremely challenging to measure directly. Includes kind of what some people call this background only or expansion only quantities, so such as omega matter. Also, it changes NS by 1 sigma. It's quite large, changing NS -1, for example, if you have higher tau. And it also affects other combinations you might think are independent. So is the determination of omega matter from ACT or WMAP plus ACT independent of Planck? No, it isn't, because it's still relying on the Planck optical depth. And I think, so even when you read WMAP or ACT combinations, they still rely on the low L polarization. So these statements in this table are still true. So it is a possible, why don't we have any evidence? We don't have any evidence that there's any problem with the Planck low L polarization. This is a possible single point of failure that in everything that we have discussed. So I think it's important to keep one mind open. And the last slide, the last thing I want to say is that this is a kind of updating some plot by Dan and others. In a previous paper, this is a history of the tau measurement. This in blue is WMAP. Up here, they have polarization data, so it's quite a bit higher. Then they have WMAP polarization. Then Planck started off by using WMAP polarization, so that's why this point is up here. And then they kind of changed when you switch to the HFI instrument, it changed quite a bit. And so this is kind of current state of the art from CMB polarization measurement. However, you can turn things around and you can say, well, within lambda CDM, so assuming a model, okay, lambda CDM, I can use the BAO and CMB lensing data to actually remove, I just remove remove the low L polarization and I fit everything else, I can solve for tau if I ask that neutrinos have, at least a mass of 0.06 or larger. And this is the value that we get, okay, in this paper. As I said, and this is formally intentions over 3 sigma tension with the value measured by Planck from the low L polarization. Okay, so as I said, we have no reason to be skeptical of the Planck measurement, but at the same time, within lambda CDM, I think this is also a bona fide measurement, and I also don't think we have any good reason to doubt this measurement. So within lambda CDM, we are staring at some sort of tau, or some of these tensions that you're looking at might be rephrasable in terms of attention the value of optical depth. So is this the right solution or not? Of course, I don't know, but it's one fun kind of possibility to keep in mind. So I'll stop here and happy to take questions. Thank you.
Thanks, Simone. I will say it's a great strategy for running long to pander to the interests of the moderator. So well done. So I have a couple quick questions. So and then I have some prepared questions as well. So Daniel, do you want to start?
Yeah, sure. So yeah, I guess I have a question about how you talk about this, right? So if I understand what you're saying is there's about a 2.5 sigma tension with lambda CDM.
Yeah.
So it seems like, yeah. So in that kind of situation, pretty much any theory that you propose that adds another parameter is going to improve the fit. So I don't really understand why we talk about this dynamical dark energy thing at all, right? I mean, couldn't it be almost anything? That's question number one. And question number two is actually, if it's only 2.5 sigma, shouldn't we really just say that it's consistent with lambda CDM and leave it at that?
Yeah, those are great questions, and I mean, I tend to agree with you, with the caveat that there is more data. So, for example, there is the supernova data, and W0 WA is the minimal model, or the minimum amount of freedom that allows you to have a good fit simultaneously to the CMB and DESI data and supernova at the same time. So if you only were taking, DESI alone, as I said, there's a mild preference for, at the 1.5 sigma or something for dynamical dark energy, but nothing to write home about. With Planck, it's more like, 3 sigma. So now you start thinking maybe I have to do something, but does dark energy have to be? I mean, I just gave you an alternative to time evolving dark energy. Which one is the correct one? I don't know. It's important to keep an open mind. Dark energy does, dynamical dark energy does improve the fits to all of the data sets, but other things do too.
But I feel like anything improves the fit if you have a 2.5 sigma tension and you let a parameter vary, right?
Yes, then does it improve enough in terms of delta chi-square versus the number of parameters that you've added? And it is quite this W0 WA. While I'm not a big fan personally of it, it does improve the fit. The improvement in chi-square is more than justifies 2 extra parameters. Let's put it that way. It's not just the chi-square the chi-square is mathematically required to increase when you have more parameters. It improves by a large enough amount that it justifies 2 extra parameters, put it that way. Once you include the supernova, I should say.
I think just a quick comment. It is also relevant that if you just add W naught, it doesn't prefer a non-trivial. So just adding one parameter is an example, or it doesn't help.
So it's also kind of this line. So if you draw a line here, which it looks like this degeneracy direction is around this mirage kind of dark energy direction, which you keep the distance to the CMB constant. When you are along this line. So it's kind of W would you would just, if just fitting a W, you get -1. Now if you leave more freedom, you get some preference. Yeah.
Okay, quick question from Andre.
Okay, just a question over your comment about tau and the possible increase of NS. I did not got exactly the way of it. If you interpret tau in the way you suggest, will it further increase NS as compared to what was discussed in the previous talk, or it is this increase which can be attributed to, so it will be kind of returned NS back?
You further increase tau by about 1 sigma, the 1 Planck sigma.
So you
increase NS by, sorry.
So you need to increase NS by 1 sigma. So NS minus 1 goes down by a non-trivial amount, if that's the question, yes.
I see. Okay.
This actually, I want to add on to Andre's question, because this was one of my prepared questions. And I'm going to start with Colin, but both of you can respond.
I'll stop share. Yeah.
Is that so? When you look at, say, so I know there's a lot of interest in NS, as indicated by questions already, but when we look at, say, expanding the parameter space, for example, to allow for, say, changes to the BBN, or changes to the matter content of the universe, we see that NS can be freed up in both directions by a pretty significant amount. So I know that was in the DR6 paper, that they show, like, say, when you marginalize over helium, you can get down to like 0.9 for NS or something like that. So with unknown parameters, with expanding the parameter space, it can change a lot. So given the tensions, and say the examples for how we might solve these tensions, either by a systematic that might shift a parameter by a small amount, or by new physics, like how much are the, say, inflationary parameters sort of reliable given the current uncertainty? So I'm going to ask both of you, but I'm going to start with Colin. Like, what do you think about, say, do we really think the inflationary parameters should be taken seriously right now, given this tension with DESI?
I think it's a fair point that the inference of the inflationary parameters, of course, depends on our model of what the universe has done after inflation, right? I mean, lambda CDM remains the minimal model. I think personally, I'm not convinced that it's overturned just yet. So, we present everything as an inference within the context of that model. Of course, one is free to extend it however you want. You could introduce some new light relics. You could change the dynamics of recombination. You could introduce some more complicated dark sector. That will be partially degenerate with some of the inflationary parameters. Some models are worse than others. Models that change the tilt of the damping tail, generally you're going to be more degenerate with NS. So things like changing helium, for example, of course, that's going to be degenerate with NS. So I mean, if you want, I mean, one way you have to place some kind of personal prior on what you think is reasonable or not. If you think some of these extensions are very reasonable, then you should be kind of doing a theoretical marginalization over those extensions and assigning some larger systematic error bar, if you will, on the inference of the inflationary parameters. But
maybe to push you in one direction, though, if you think this, so you sound skeptical in the failure of lambda CDM. So then I presume that you would just interpret this as a 2.5 sigma or 3 sigma statistical fluctuation. Should we then say that, again, but that could then mean a 2.5, 3 sigma fluctuation of NS is very plausible, given the degeneracies within these types of parameters. Do you think the fluctuation, if that's your interpretation, should we think that maybe until we resolve this, we should just expand the space of parameters that we think are the true ones, or are there more plausible directions than others for this resolution?
Well, so first on the question of lambda CDM, so note that one has to choose a particular supernova data set to ever see evidence that it's greater than a 4 sigma, failure of lambda CDM. If you choose the canonical supernova data set that we used in DR6, that was the most widely used in the community up to that point, which is called Pantheon Plus, the evidence of dynamical dark energy actually weakens compared to what you get with just DESI plus CMB. So I following from what Dan said a minute ago, Dan Harlow, I mean, to me, it looks like right now the minimal hypothesis is that it's just a fluctuation and that there are systematics in the supernova data sets. The other supernova data sets are far less well studied, and I think that there's people in the community who are currently looking at, let's say, the robustness of some of those data sets. But yeah, your broader point is well taken. I mean, I think we should always keep in mind that the error bars are contingent upon the model that we're using. So if I quote like, NS moved up by 2 sigma within the context of lambda CDM, it's very important to remember that is in the context of lambda CDM. And then if I adopted a more flexible model of the late time universe, that the sigmas themselves would be larger. And so, your conclusions would perhaps change a little bit. I don't think that's too controversial, but it's worth keeping in mind that that's how we do inference in cosmology. Maybe
Simone, do you have a dissenting opinion?
No, not at all. I mean, one thing in the context. Since you brought up primordial physics, I am a little bit concerned about tau, as I mentioned. I don't know if the full solution. I wouldn't be surprised if it played some role in it. Right. We do have to assume, for example, scale invariant power spectrum when making these statements. One way to reconcile the Planck measurement and having a higher tau is if you suppress large scale power, large scale modes, for example, in a scale dependent way. And you could argue maybe that's brings into there are all these large scale temperature anomalies in the CMB. If you were to see something like that in polarization 2. That might ease some of these. You will allow you to get a higher tau and lower, and still be consistent with the Planck measurement if the primordial power spectrum was scale dependent and was lower on large scales, for example. Do we have any strong evidence of that? Probably not at present, but none of the way I see it is that none of it, including an S, is completely written in stone. We do the best we can, and we try to be open-minded and test as much as possible, and then but these are hard measurements, and based on very few modes, and so yeah, we do the best we can.
Okay, I have a follow-up question for Simone, and Colin can chime in, but I do. So many people, I think, on this call will be interested in, there's perspectives of whether if it's the cosmological constant. Some people are interested in whether that you can't have a positive CC, et cetera. And then of course there's the suggestion from your data that actually if it is dynamical dark energy, it violates the null energy condition, which again, a lot of dissenting opinions here. But I guess the sort of broader question is, how would you convince the community that it is dynamical dark energy, given what we've seen here? You see something that's really seems to point to something that's unusual. I think a lot of theorists would be skeptical of the current interpretation. But let's say that was the right model. What would be the measurement that would convince people, given that it's like this, say, a couple data points on a H of Z plot? Is there some other measurement that you can do? Like, what is the thing that we would point to?
Right. Yeah. So that's a great question. I mean, of course, now the WNOWA is kind of phenomenological parameterization. So first of all, I would really caution against the kind of extrapolating of what the universe was doing, at very high redshift, for example, based on this simple parameterization is a phenomenological model. Yeah, exactly. I want.
Can I ask you to comment on this plot though?
Have that. Yeah. So I mean. As you can see, the quote unquote evidence that it ever goes in the phantom regime is probably, by I less than 2 sigma, right? You can take it for what it is. I mean, those error bars are representative of of the status. Those error bars will be shrunk significantly by better BAO measurement. They will be shrunk significantly by going to higher redshift with future surveys. I should say that the supernova data is quite constraining if you take it at face value, right? So improvements now there are new techniques in the supernova world, like this twinning between photometry and spectroscopy that seems to reduce both systematics and scatter quite a lot. It's an evolving field. We're collecting data fast, but you asked really, what would it take to believe it, and then consistency between multiple data sets is, if the difference only comes from, comparing, BAO to CMB, well, that's, 13 billion years of the, cosmic history. There's a lot of things that can happen in the middle, which are not dark energy, like weird dark sector interaction between neutrinos and other particles. There could be a lot of explanation, and really be sure that it's dark energy. Of course, it's really hard, right? And I think if multiple probes, you make predictions, given a particular dynamical dark energy model, and you see it in multiple probes independently at different stages in the history of the universe, then I will start to believe it. One thing that I'm working on is how do you independently, we've seen that neutrino mass and dynamical dark energy are quite intertwined, is there a way to disentangle them or kind of orthogonalize their measurement? This is something we're, for example, working on right now, and I think you can probably do it. So, yes.
Okay, thanks. I'm gonna let Colin answer. Do you have any comment?
Yeah, I can give two brief thoughts. So or maybe I have three thoughts. The first thought I have is okay, if you really want to confirm that it's dynamical dark energy, I think there's at least two things that are interesting. One is that you'd like to see confirmation from probes of the distance redshift relation that both do depend on early universe physics and then that don't depend on early universe physics. So the supernovae are important here because they don't depend on the early universe physics. I think that the systematics there are still maybe difficult to assess. But one cause for optimism is that there are other probes of the distance redshift relation. So strong gravitational lensing measurements are improving. Hopefully, gravitational wave-based measurements of distances are going to continue to improve, either from binary neutron star mergers or maybe these dark sirens with binary black holes. So over the next 5 to 10 years, I think we'll get independent pictures on the distance redshift relation. The other thing that I think would be nice, though, is that if it's truly not a cosmological constant, then as soon as W deviates from -1, there has to be perturbations in that field. And in principle, those leave signatures in structure formation. So if we could convince ourselves that we were seeing a consistent picture both from the perturbative dynamics and from the background dynamics, I think that would be pretty conclusive. As far as confirming the current, or what I think about the current results, it is the case that you can reconcile DESI and the CMB with a variety of different extensions, not just W0 WACM. You can change any of the physics that changes the drag scale or the sound horizon in the early universe. For example, modified recombination, early dark energy, a wide variety of things, because you're just changing an overall normalization, and that actually eats up most of the difference between DESI and the CMB. Those extensions don't work for the supernovae because they don't depend on early universe physics, which is why they're useful at all. But yeah, as far as the current data goes, I'd say there's a landscape of possibilities. It certainly doesn't have to be dynamical dark energy.
Okay, awesome, thanks. I'm gonna now go to the questions. So I'm gonna go through an order which I saw them at least. So I think Mark has the first question.
Yeah, I guess I just wanted to maybe advocate for a point of view. So I think if there were dynamical dark energy, I would say from a theoretical point of view, there's a really simple, maybe the simplest model of that you would get from some effective field theory is just the standard kind of changing scalar field. And so if we take that point of view, I would say that there's a natural way to parameterize deviations from lambda CDM, which is just to maybe kind of focusing on late time. We don't really know what the potential would look like, but we do know that whatever function it is, you could Taylor expand it around whatever the present value of the potential is. And so this is something that I talked about with Chris Waddell, that I think a natural thing to do is just to think about the Taylor expansion of a current potential, and you can work to linear order or quadratic order. And then maybe kind of focusing on late time data. So if it's some complicated potential, at least in the fairly recent past, you might think that Taylor expansion is going to be valid. And so at least in our preliminary analysis with just like supernova and BAO, it seems like there's a similar significance level, similar kind of discrepancy with lambda CDM when you have some this just linear scalar field model, and so there I think there's no question about like violating energy conditions. It's just a totally sensible physical model. So I think, to me, if you ask what would be convincing, just looking at late time stuff, and then finding that these Taylor series coefficients in the potential would be just like not having non-zero values for, say, the slope, that would be fairly convincing to me.
Okay, yeah, that's great to hear, and I think there were some related papers like by Paul Steinhart's group, right? That showed that for DESI year one, some quintessence models that don't violate null energy conditions, were in good agreement with the data or could fit the data well.
Stefano?
Rafael has a question. Sorry, yeah, I'm borrowing Stefano's computer. I guess I saw the question maybe flash in the chat from Daniel already, but I want to ask it anyway. How would we ever rule dynamical dark energy out? And I think he's asking it for the same reason that I want to, which is that I think the answer is never. It's like asking how will we ever be sure that the moon doesn't contain cheese? How deep do we have to drill down before we're 100% certain? We've already come from like W is somehow less than -1/3 to a couple percent from -1, and seen no sign other than tangents that come and go, and which will naturally always keep coming and going because cosmology is hard. And so I guess I want to ask a meta question, which is why is it not okay to measure the universe because it's interesting? Why do we have to pretend that we're trying to discriminate between two equally plausible theories when that's just not the case? And related to that, when you say you add one parameter and you're looking at how much the fit changes, we need a better way of capturing how insanely fine-tuned that parameter actually is. We're not counting that fact. When we present it as W and W naught, WA, and stuff like that, we're suppressing the fact, and here I disagree with Mark, for example, we're suppressing the fact that in the real world where supersymmetry is broken, the kind of potentials that we need require insane amounts of fine-tuning to give us dynamical evolution over billions of years, to make sure they don't show up as a fifth force. And even then, I don't understand why we haven't seen it yet. I mean, we've already covered so much in terms of even this W plot. So that would be my comment.
I could offer a quick response, maybe.
Go for it.
I think, there's two ways of framing the question. One of which is, I think what Daniel asked in the chat was about excluding lambda CDM. I think that's a far more well-defined question,
Yes.
and that we can actually answer that if it is going to be excluded, right? You can just say like, this is a well-defined model with 6 parameters, and does it fit all of the data that I have? If we find it within a few years that eventually it really convincingly doesn't fit all the data, that's a very well-defined question. The harder question then is to say, what's the correct model beyond lambda CDM? And there, I think it will be a much, much harder task to narrow down on what it is.
Sorry, sorry that I
Maybe-
mischaracterized Daniel's question. I only saw it flash by in the, but I think my question is a valid one, because I mean, if we were so lucky to see like a really clear, clean violation, and we've got all our systematics sorted out of lambda CDM, then we can just go and study that, and the whole world will like
For sure.
go up with excitement, and it's going to be amazing. The problem is that is something we've been doing for 25 years now, more actually, and we haven't seen any really reliable thing. We've seen these fluctuations come and go. People have pointed out here, like which supernova catalog you use matters. Who knows about the optical depth? There's all these things. Like, I don't believe for a second that this is a real tangent. And so my question is, when are we ever going to stop and say, that's not what we're doing? We're not after this like hypothetical thing of lambda versus dynamical dark energy. When are we going to be done?
Well, I do think it's a fair question to say, how close to W equals -1 do you need to get that error bar before you decide that it's close enough? Because there's not a clear threshold, as far as I know. So I think that's a fair point. I mean, in my opinion, a different perspective on this is that we should go out and map the universe to the best of our capabilities. As a byproduct of doing that mapping, we do learn about potential new physics of this sort, but it doesn't necessarily have to be the motivation for doing the mapping.
That's exactly the perspective I would like to advocate. I think it's extremely unfortunate that we seem to have to justify these beautiful observations in terms of what I think is effectively a smokescreen of like some equivalence between different, or we have no idea what dark energy is. Let's call it this mysterious dark energy, right? It's unfortunate. It's maybe that's how the game has to be played. Maybe that's how you get funding, but I think it does distort the science a little bit.
But can I jump in here? So I mean, I completely agree that, I mean, but none of, I can speak for myself. I cannot not represent the collaboration, right? But, I'm not in this game because I really care about, what's the value of WA or, at some, and whatever. And I should say, DESI has, about 200 papers published, about, 560 projects declared on the, on the publication database, and, 3 are about dark energy or something, like, the time evolving dark energy. And so there's so much science that we can do. But I do feel like, at the 3 sigma level, and if I can share my screen, maybe I can, make this point. There is some, if we believe the CMB, and then let me see if I can show this, right? If we believe the CMB, okay, this is the measurement of DESI, and this is what, it should be in lambda CDM with, CMB parameters, okay? And by eye, I see, a deviation. Now, is this like, null energy condition, phantom dark energy and everything? I don't know, but you agree that if these error bars got smaller, then I can start saying, okay, we have a problem, right? And I don't know, and I try to be clear that I don't know what the solution is, right, during my talk, but I can point out that there's a problem. And by the way, the supernova problem is the opposite, right? So, if you had the, I made the statement that lambda CDM is a good fit, it's still a decent fit to DESI, just with slightly different parameters from the CMB. Once you throw in the supernova, they want to go in opposite directions, right? And that's why you need to open up the parameter space if you want to solve it with dark energy. But I think I've tried to be clear that, while that's one way, we are far from having a proof that that's, the correct answer to the data is what I'm showing you on the screen, and I think it's fair to say that either we have systematics or there's something that doesn't quite fit, and these error bars will get better and we'll know more, right? And that's how the cosmological constant kind of experimentally came about. There was some cluster abundance didn't quite match. There were lots of indications for low omega matter and then supernova, and the evidence kind of started off with some mild tensions, and then it kind of built up. And here I see some mild tension which may go away and may stick. We'll see.
No, there's a big difference. I mean, I remember the discovery of the value of the cosmological constant. The big difference is that there was never any prediction that the cosmological constant was 0. So there was no rational reason to start with that assumption and then like be totally shocked when it wasn't. There was simply no good explanation for its smallness. And so all we could do was measure its value, and somebody did, which was great.
Okay, I want to make sure we get to the next questions. I just want to add one comment for the people in the audience. Which is, I think part of the reason Simone talks so much about neutrino mass is a thing that we expect to see cosmologically at 5 sigma in the coming years. It has a prediction from particle physics that's supposed to be non-zero, and we're supposed to see that number. And that's why I think people have focused on that, because it's like, hey, we are supposed to detect that. That's not a just parameter we added for no reason. And that's the thing we should definitely be able to see with quality data. Anyway, I think this could go on forever, so I just want to make sure people knew that that's why that was a topic that came up. But I want to make sure we get to Eva and Igar. So Eva?
Okay, sorry. Yeah, sorry, my comment and question are a bit trivial compared to the deep discussion we just had. But coming back to the NS story, I mean, an obvious thing one can do is plot not just the 1 and 2 sigma contours and the zoo of categories of inflationary models, but also 3, 4, and 5 sigma contours, and see how those change as we add the ACT data. And, that would be a trivial thing for, Colin to do if he wanted to do. That, plot, which we had generated by the bicep folks here, does already have some power to constrain things. We all know the tilt is discovered already at that level. And, constraints on, say, m squared, phi squared remain if you go up to 5 sigma. That's all true. So the obvious question is with that and with SO coming and also with this comment from Simone about tau, like what are you guys' forecasts for how that's going to tighten? The reason people are so interested is because the 2 sigma probabilities, have jumped around a little bit and, they're changing, which, broad categories of inflationary models, look more preferred. But regardless of the standard we use, go up in your sigma standard if you want, like what's next for let's say for NS and power spectrum in general features and all that.
I can give you a few benchmark numbers that I have just on the top of my head for SO, Simon's Observatory for those who aren't living in the CMB world. So Simon's Observatory will measure both the high L CMB like ACT has done, but even better than ACT. But it will also measure the low L polarization, beam mode polarization with a different type of telescope, these small aperture telescopes. So we'll improve constraints on both NS or also the shape of the power spectrum in general, and also improve constraints or maybe detect primordial tensor modes from beam mode polarization. So the constraint on NS from SO, the projection is that it should improve the existing constraint by about 50%. I think that was with respect to pre-ACT-DR6. So probably it improved it by something like, 40% compared to maybe 30 to 40% compared to the current data. And then R, we're expecting to improve constraints by quite a lot. So by the early 2030s, with the SO small aperture telescopes, we should improve the sensitivity to R by about a factor 10 compared to current data. And if we run through the mid 2030s, then I think it should improve by another factor of 2 or so beyond that. So we're targeting sigma R of order 10 to the minus 3 with the full SO data set by the mid 2030s. So it should be highly constraining on inflationary models.
Great, thanks. And the thing about tau, is that going to get better, or is that just some systematic that nobody's ever going to understand?
Tau is a harder one. We don't have an upcoming instrument that is designed to measure the lowest L modes in EE. There's an instrument called CLASS, which is trying to do this from the Atacama. They've released some preliminary results that it looks like it kind of is working, but it's a very difficult measure from the ground. I think the best hope is that the Lightbird mission gets approved and that Lightbird flies in the early 2030s. It would measure tau to the cosmic variance limit. So that's, I think, the cleanest hope. It's also possible we can measure tau from astrophysical probes of reionization. Simone and I have written some papers about this with other things like the KZ effect or 21 centimeter measurements. But then you have to have an astrophysical model of reionization to translate that to a tau constraint. And then it becomes an astrophysical thing. And as we know, that's like super complicated. So we'll measure tau directly with Lightbird. Yeah.
There's also some balloon proposals that might be, some middle ground, but yeah, not clear.
Great. Congrats on the results also, everyone.
Thanks.
Okay, I'm going to save it. So last question is for Aigaran, and so please go ahead.
Hi, thanks, Colin and Simone, for the nice talks. I just want to ask, so what's the reasoning for maybe not considering other models that are like just slightly away from lambda CDM? So, and like, for example, primordial curvature and stuff like that. Is that just something that couldn't explain some of the results that we've seen that seem similar to the early dark energy? I know we discussed a bit, Colin, regarding the oscillatory features in the PPS, but yeah, I was just
so we do constrain omega k, just the large scale spatial curvature. I didn't include anywhere near all of the results from ACT-DR6 in this talk. The constraint on omega k from Planck plus ACT plus DESI DR1 is consistent with 0 at 1.5 sigma. The error bar is around 0.2%. There is a small hint in DESI DR2 of non-zero curvature. I don't know if somebody wants to talk about that. It can partially reconcile the DESI CMB mismatch.
Yeah, I mean, yeah, it's another thing that that could potentially, alleviate some of the tensions we talked about. Not so much with neutrinos. There's other things there, but yeah.
Which way would it be going? Sorry, would it be omega k negative or positive?
An open universe.
Okay, open you. Okay,
Yeah.
okay. This was also so yes. So this was like back in 2019, I think it was, when there was like this potential curvature tension rate, which got a bit of publicity before the Hubble tension, but the curvature tension I think was moving more towards a positively curved universe, right?
Yeah,
This was
this is the other way. Yeah.
yeah, exactly. Okay. Uh, and yeah, so positively curved would end up making things worse in terms of the tensions that you're seeing. Okay.
Yeah.
Thank you.
All right. Thanks, everyone, for your patience going long, and to our great speakers, Colin and Simone, who did a really good job summarizing the state of the field and provoking some really interesting discussion. So I hope all of you will stay tuned for future data. I think we don't have a plan to have talks over the summer. I think that Mark could confirm, but anyway, thank you all, and stay tuned for emails on updates to this meeting. Mark, do you have any more announcements?
Yeah, I don't think I have any more, but we're going to plan to continue this, but probably after a summer break. Thanks for everyone to show up, and we've had some really good discussions, so it's been great. Thanks.
Thanks a lot.
Thank you very much, everyone.
Bye, everyone.
Ready?